Now in this session, we talk about some aspects of dynamic models. More specifically, we'll focus on the approaches to dynamic modeling. Now, before going into the approaches, let's discuss about why do we need a dynamic model. Now, do remember that the aspects we'll be talking about are directly relevant to process control. So modeling approaches, use of models, and the need for models can be very different for different fields. So the discussion in this talk will be focused on process control. So let's look at, for the purpose of control, we need the controller to know how the process responds when there is a change made. Now, this information can be fed to the controller in different ways. For example, say a PID controller, the parameters of the PID controllers are obtained using the model parameters. Now, another case for suppose the model predictive controller, the dynamic model is used to predict the output and decide the input signal based on the predicted output. So there are two different uses. For both cases, we need an explicit dynamic model of the process. So in the field of process control, those are the main needs for dynamic models. Now, how to get a dynamic model? Now we'll discuss two main approaches. The first one, let's look at what is called this first principles modeling. Okay, so the basic idea here is that we need to use the laws of nature. Why? Because the behavior of the processes are governed by the laws of nature. So suppose, let's take an example that what will be the flow rate of a liquid through an outlet. It depends on other characteristics, but also on the gravitational force. In a reactor, how two reactants reacts, that's defined by laws of nature. So there are scientific principles describing those laws of nature. So when we use those scientific principles to get a model of the process, that's what we call this first principles modeling. So in particular, in first principle, we use the conservation principles. And along with the principles of thermodynamics, mechanics, kinetics, and heat and mass transfer, formulate the main equations. So we'll talk about the conservation principles in details later in the talk. But first, let's take a look at a 5-step approach to first principles modeling, how it's done in reality. Now, depending on there is nothing like unique in this number 5 here. Just you can define the steps in any suitable way you find to be convenient to remember. But just we have defined in this case like a 5-step modeling, and we'll discuss the steps one by one. So a modeling exercise starts with defining the objective. Okay, remember the scope of this modeling in the context of process control is to define what is called this input-output relation. So that's the scope, the input-output model. It represents the output behavior with change in the input. Okay. Now, first we need to identify the model objective, meaning what are the input-output pair, and also need to identify what's their link, how they are related. So that's the step 1, defining the modeling objective. The step 2, very important step for this modeling exercise, is to gather process knowledge and information. Now, this model will be based on the process knowledge, and for those cases we need to know the knowledge about the mechanics of fluid flow, about kinetics, about mechanisms for heat and mass transfer, and so on. All these aspects should be known. So these are fundamental principles that governs like the process behavior can be described by those principles. But there are other information also needed. For example, the equipment size, how the flow outside it through a tank, through a pipeline from a tank is determined by not only the valve characteristic, also by the tank characteristics. So definitely level of liquid in the tank as well as other parameters will define how the outflow depends. For reactor, how this reactor temperature will depend on the steam flow in the steam jacket, will depend on the volume of liquid, so volume of the reactor. So all of this equipment sizing becomes important. So we need to have relevant information about the equipment as well to get a process model. Now the step 3 is the main step that most time is spent, which is called developing the model equations. Now, depending on the input-output pairs you will have to use the appropriate conservation principles. So that's the first thing. And then the relevant kinetics, fluid flow model, or heat and mass transfer model, along with those conservation principles to formulate the main model equation. Now, typically, when you develop a model from first principle, the model may be too complicated. And for the purpose of control, we need a simple model. Okay. So later we'll see that, okay, we'll need at the end either first or second order, what is called this linear ordinary differential equation model. So you have to convert those complicated model obtained from the first principles and using other governing equations into a simplified equation that will be useful. Okay. So one aspect you need to remember for modeling is that, okay, you need to have a useful model. So that depends on what's the use of the model. If you are getting a very complicated model that cannot be used for the given purpose, the modeling exercise is not fruitful. So that's simplification, and then expressing it into standard form. Okay, this is very important because for controller design, we need the models in standard form. So we need to have that standardization. Okay, and the last step is to analyze and validate the model. At the end of the modeling exercise, you need to show that the model that you developed can really predict the output. For this case, you may need to solve the equation you got and then compare it with some sort of process information. So now if there is an existing process, you can get some data and validate against those. If the process is not available, you can at least have some qualitative validation that will give the direction of change and to some extent that how much change can be made. So need to validate the model against process information. One very important thing is that when you standardize or simplify a model, that model may not be valid over the entire operating range. So you need to define the operating range over which the model is valid. Okay. So this is a 5-step approach that we follow to obtain process model using the first principles. Now let's take a look at the approach again. So the figure on the left presents the what is called this first principle approach. So here you see is starting with the objective, and using the first principles you get what is called as model structure. So when you use the first principles, meaning the conservation principles along with the governing equations, that gives you a model structure. Again, this can be complicated. Now then you need the process knowledge. So this is what has been defined as step 2 in the steps. This is 1 and this is 3. Okay. Now using the process knowledge and depending on the need, you need to simplify the process to get what is called a simplified model. Now using the process knowledge and data, you get the model parameters based on the simplified model structure. Now this simplified structure along with the model parameters formulate the process model altogether. So that's what step 4 in the procedure. And then use the model for some sort of prediction and then compare it with some process data to get the model validated. Now this is one approach. What you call this is first principle approach. What may be the other approaches? Now you remember that the objective of this modeling exercise is to develop a model between the output and input. Now if we have a process, if we have some process data, can we do some mathematical, can we take a mathematical approach to just do some sort of curve fitting to find a model for the process using the data? And that's the approach what is called is system identification. So this is what is called as data-based approach. So again, you need to define the objective for this case, and what you need is the process data. So process data and enough process data to obtain a useful model for this case. And also the process knowledge is always required because that will determine that what type of equations you try to fit. So with process data and process knowledge you get some sort of like model structure. And then for that particular model structure and using the process data, what you get? The model parameter. And this may be a curve fitting approach. So we can have for the process data, we already have, say suppose some sort of input and output data. From there, you can get the model parameters, and from process knowledge using process data, you can get the model structure, and all three together. So model structure and model parameters gives you the process model. And then you can again have some sort of solution of the model to predict the output and then compare with maybe another set of data to validate the model. So these are the two approaches that we will take. First, we will take the first principle approach, how to find model using the first principles. The second case, we will see that for many cases, the first principle approach may yield some model which may not be useful. However, using data, we can get simplified model for the process. So in summary, there are two approaches. One is first principle that uses where the model structure is typically obtained using the first principles, and then model parameters are obtained using process knowledge or the system properties. The approach to system identification, where the model structure is iteratively determined from process knowledge and process data. The model parameters are estimated using input-output data. This is a totally data-based approach. Okay. Now we talked about the conservation principles. So let's take a look at the laws of conservation, or what are called also known as the conservation principles. So in terms of energy and or mass, the principle states that energy or mass cannot be generated or destroyed. It can only be converted from one form to another. Now, we need to take a look at this statement from a process control perspective. And if you are analyzing from, say, suppose the Einstein's theory, E equals mc square or something like that, we are not going into that level because the conversion between mass and energy we are not considering here at all. That may not be relevant for our case, and the effect of that can be very minor. Okay, so we're considering that the energy cannot be destroyed or generated, and so as mass. Okay, so there are three principles. What is called this conservation of mass, conservation of energy. The third thing is that conservation of momentum. Now, do remember one thing: for control purposes, the conservation of momentum is rarely used. Conservation of energy is when temperature is one of the variables involved in the modeling exercise. But most cases, the conservation of mass will be there for all of the cases. Now take a look at the conservation of mass. So I'm not going to details, just about discussing the equations relevant for our case. So there are this overall mass balance. Okay. So it simply says that if there is a steady state, this term would be 0, meaning that there will be no accumulation. So in will be equal to out. But when there is an accumulation, then that rate of accumulation of mass will be rate of mass in minus rate of mass out. Now do remember one thing, always write the equation in terms of mass. That's very important. Okay. Now just to give an example about rate of accumulation is that if, say, suppose for in any program the number of intake students is a certain number 100 and the number of out is, say, suppose 80 or something, so it's not at a steady value. Okay, so there are, say, 20 students accumulated within the program, meaning that they either fail to graduate. Okay, so that's the example of accumulation. So mass in a steady state, mass in will be mass out, but when there are accumulation, then the rate of accumulation of mass will be rate of mass in minus rate of mass out. Again, always write the equation in terms of mass. Now what about the component balance? Now for components, it will not be simply rate of component in equals rate of component out, not the case. Okay, so if there's an accumulation, so we're talking about dynamic scenario, meaning that it's not a steady state. So in dynamic scenario, there will be accumulation. So the rate of accumulation of a component I will be rate of in minus out. That's understandable. But this component can also be generated through reaction or can be consumed in a reaction. Okay. So when you're talking about the component level, these two additional terms come into play. Now let's just give an example that if you're having a class, the intake was, say, 100 and the out was, say, 80. So that gives you the rate of accumulation 20 per year, whatever way, for an overall mass balance. So for the component balance, suppose you have 100 students came in and, say, 80 got out of the program. So there is an accumulation of 20 some per year or whatever way you define it. But now in terms of component, if I divide the entire class into, suppose, married versus single or something like that. So you can think about during the course of this program, some married students can be returned back to their single status, or some single student can be, get married. Okay, so that's how these two terms comes into play, that rate of generation of I, rate of consumption of I. So if some of the single student got married, so this will, for if we are considering this I to be the married students, so the single student get married, so number of students got married, so that's the generation of I. And the rate of consumption is that for out of this married student who becomes single again, so that will be the rate of consumption. So you can think about in this way, if you have a set of reactants and reactants are being consumed to produce a product, also like from the reverse reaction or through another reaction, the same species is being generated, so that will be taken care of in this rate of generation and rate of consumption term. Okay, that's the component balance. So let's look at the conservation of energy then. Now for the energy term, again, we'll have the accumulation term, so rate of accumulation of energy that will lead to change in the temperature of the system. So energy is coming into the system by convection through fluid coming in. So whatever energy, so in terms of internal energy, is being brought by the incoming fluid, that's the rate of energy in by convection, and the fluid is going out. So that energy that's going out of the system by convection is called the rate of energy out. So those are understandable. What are the other terms? If there is a reaction, so heat can be generated by the reaction. So that should be taken into account because that will be causing an increase in the temperature in the reactor. And then there can be something like heat addition. For suppose an endothermic reaction will need to add heat, and that should be taken into account. And finally, the rate of neat work done. So typically, if there is work done on the system, that needs to be taken care of for the overall conservation principle. Now, for many of the cases, we will see that the last term may be least used for process control perspective. However, the rate of heat generation by reaction and the rate of heat addition, those are very important and should be taken care of. Okay, so those are the summary about these conservation principles. Now, let's look at what are the model that we'll be using, the model that will be getting, what are the use of this model. We talked about a little bit on the controller perspective. So for controller design, for some controller, for the PID controller, the parameters of the controller directly obtained from this model parameter. So that's the direct use of the model. For say controller like model predictive controller, so the prediction using the model is used to determine the input signal. Okay, so that's another use where for both cases the explicit model is required. Now for other cases where model are used is for process simulation. Suppose we cannot do experimentation with a process to get data for all possible operating conditions, because some operating conditions may lead to unsafe operation. So in those cases, we cannot run the process at that operating conditions. However, you can use simulation to know the process behavior of those conditions. For monitoring or failure prediction or diagnosis, suppose you can run the process at different conditions and look at whether the process lead to some failure conditions or not, and then need to diagnose this condition using the data. Models can be used to train operators, meaning that you can simulate some sort of abnormal situation and determine what control action helps to overcome those abnormal situation. And also for a startup and shutdown, this situation can be simulated and then the operator actions can be determined using simulation. And finally, the process optimization, that you can collect data for a wide range of operation, and then using all those data, you can have proper optimization of the plant using those information. So in summary, from controller design to simulation to operator training to process optimization, models can be used.